So I'll try and make this short and sweet. We got interrupted today in class because of the fire drill, so I wasn't able to finish. But I want to be able to give you something quick you can just look at, and hopefully will tell you what you need to do for simple application of derivatives and antiderivatives when it comes to motion equations. So I want you to imagine, real quickly, something we've already talked about, and that is if you have a graph, there's meaning to the slope and to the area, and you need to test for both. We've been doing a lot of work with velocity graphs. And for a graph like this, talking about what the object might be doing is pretty straightforward because you know two important facts. First, the slope of this graph is acceleration. And the area of this graph is displacement. Well, you know something else too, because we didn't just talk about those graphs. We also talked about graphs like this, position graphs. And if we want to have a position graph that matches up with what we've just drawn, then looking at what's over there for what we've just drawn, starting, assume at the origin, ending same amount of time later, then probably have something like this. Oops. Some kind of parabolic path. Positive slope at the beginning, positive slope at the beginning. Negative slope at the end, negative slope at the end. Zero velocity in the middle, zero velocity in the middle. And we can talk about all those things because we also know over here, the slope of this graph is velocity. Well, up here in the velocity graph, finding the slope would be easy because just pick any two places. The line is straight, so we can find the slope, which gives us the acceleration, by doing delta v over delta t. But it's more confused over here, where if I take those two spots, one slope, I take these two spots, I get a different slope. And if I take this spot and this spot, well, that wouldn't make any sense. The slope's changing over here the whole time. So it's difficult. We know that the velocity is the slope of this graph, but it's not a constant. So I can't just write delta x over delta t and it'll make sense. It doesn't. This is what calculus does. Calculus is the algebra of functions. It will create a new function from a function you already have. I'm not getting into the specifics. You'll take calculus, you'll learn the specifics. I need you to be functional. So over the course of the year, we're going to learn how to take the derivative. The derivative essentially produces a new function. So if I know that acceleration is the slope of the velocity, then instead of taking the slope using rise over run, I'm going to transform this and write it as d dt of the velocity. This is saying I'm going to find an expression for all the slopes of the velocity function. That's what taking the derivative will do. This can also be written as we're taking the deltas and changing them to a lowercase d. That also means that velocity is going to be d dt of a position function. It's going to take the position function and create a new function that will tell us all the slopes of the position function, meaning it will tell us the velocity. Now, taking the derivative is a process, and there are rules for this process, and it's all based on the fundamental theorem of calculus. However, most people don't apply the fundamental theorem of calculus every time they take the derivative. They use a rule that they have already been shown works using the fundamental theorem of calculus. I'm going to teach you over the course of the year all 4 rules. I want to teach you the polynomial rule, I want to teach you a rule for sine and cosine. I want to teach you a rule for the natural log. And I want to teach you a rule for exponentials, because those show up in our class. For right now, you're only going to be learning the polynomial rule. So, we're going to learn two different forms of this rule. We're going to learn what it means to take the derivative using this rule. Then we're going to learn to go backwards and take the antiderivative. So basically, consider it this way. If taking the derivative of the velocity produces the acceleration, going this way will produce the derivative and give us acceleration. But sometimes you may want to start with acceleration and go this way and go back to velocity. Well, that's going to be finding the antiderivative. But I'm getting ahead of myself. Let's start with polynomials. Now, I learned a valuable lesson, polynomials, that some of you don't know what polynomials are. So here is a polynomial. Polynomial is just any group of numbers that are being added together. And whether those numbers be numbers or symbols, it doesn't really matter because a symbol just represents a number. So in this case, I have a polynomial. Now, if I want to take the derivative of a polynomial, you'll notice that when you go to take the derivative, you are going to have something in the denominator that's telling you what the important variable is. So if I put d dx, then what I'm saying is take the derivative of this function with respect to x. X becomes the important variable. It's a functional variable. Anything else is treated as a constant because we're not doing anything complicated math. So c, bc, 5, and -3, they're just constants. X is the functional variable. But if I had written this as take the derivative with respect to c, suddenly c is the functional variable. That'd be the one that'd be important. I'd focus on c. Everything else in here would be considered a constant. So when you go to take the derivative of a polynomial, you're going to have a functional variable that's important. But the process is pretty easy. Let's say we're going to take the derivative with respect to x of ax to the n power. I'm only looking at one term in a polynomial because when you take the derivative, you just go term by term. So we're going to look at just this term. Since I'm taking the derivative with respect to x, x is the functional variable. A and n will be treated as constants. Now the process is pretty easy. You take the n out front, and then you subtract 1 from the exponent. Just like that. That's how you take the derivative of a single polynomial. Now, let's consider the polynomial I have here. And let's consider I want to take the derivative of this polynomial with respect to x. So we're going to go term by term, because basically you can distribute the derivative. So I'm going to take the derivative of each one of these terms. Let's talk about the first term. The first term is cx cubed. So I'm going to bring the 3 out front, multiply it by c, and I'm going to take x to the third and subtract 1. I'll clean this up in a minute, but that's my new term. Go to the next one. I'm going to bring that -2 out front. The bc stays, and then it'll be x to the -2 minus 1. Again, going term by term. Now, x doesn't seem to have an exponent, but remember, if there's no exponent there, then it's an exponent of 1. So I'll bring the 1 out front, and then x to the 1 minus 1. Now, I'll notice that last term doesn't have an x in it at all. So, if there's no x in it at all, then just imagine that there's an x to the 0 power there. And we're going to bring this 0 out front. So minus 0 times, and who cares what's next? Because we're multiplying by 0. When you bring that 0 out front, everything becomes 0. So we clean this up. We'll get 3c x squared minus 2bc x to the negative 3 plus 5x to the 0. This is my new function. So I took the derivative with respect to x, and I got a new function out of it. Calculus is, like I said, the algebra of functions. Okay, we're going to try again. So let's take a look at a function that maybe we would have. Let's say we have a position function. That is 6t cubed minus 12t to the negative 2. This is a position function. And let's say you're required to find out what the velocity of this object is at some time in the future. Well, you'd like to create a velocity function then, because you currently have a position function. So to create velocity, I know that velocity is the derivative with respect to t of the position function. Well, this is my position function. So what I really want to do is take the derivative with respect to t of 6t cubed minus 12t to the negative 2. So I'm going to take the derivative. I go term by term. So let's start with that first term. We bring the 3 down. And we have 6 already there. And now we take 1 away from the exponent. Move to the next term. Bring that negative 2 down. 12's already there. Then take 1 away from the exponent. And that's it. Now clean it up. 3 times 6 is 18. T to the 3 minus 1 is t squared. And now I've got negative 2 times 12 is going to be negative 24, but I have a negative there already, so positive 24. And that's t to the negative 2 minus 1, or negative 3. So we started with a function that was about the position, and now we ended with a new function that tells us the velocity. So I can tell you at any time where the object is, and at any time how fast it was going. But wait, there's more. Don't forget, acceleration is the rate of change of velocity. So just like the slope of a position graph is velocity, the slope of a velocity graph is acceleration. So I can take the derivative again, and when I do, I'm now getting another new function, and this new function will be the acceleration of the object. Again, following our procedure, we'll go term by term. I'm going to bring down the 2, and then I'm going to take and subtract 1 from my exponent. Go to the next term. I'm going to bring down the negative 3, subtract 1 from the exponent. Now, simplify. 2 times 18 is going to be 36t. And now 3 times 24, don't forget that negative sign, 72, t to the negative 4. So we started with one function, this one, and using calculus, we were able to generate 2 more functions. So now we have a whole profile of the object's motion. Now, going in this direction, we take the derivative. you can probably imagine there's got to be a way to go in the other direction. And there is. Going in the other direction will be the antiderivative. We're going to get to that, but I want to talk about one more minor thing. You've already kind of had this in front of you. Remember when we first started looking at this, I said, the slope of a velocity versus time graph is the acceleration. And because it was a linear function, we got this. And then I said the area of that velocity versus time graph generated something based on a trapezoid. And then we built out a whole bunch of motion equations that were based on doing mathematical substitution. But it was all from algebra. And again, this was based on a assumption that our acceleration was always constant. I want to take a look at just this and this for a minute. First, let's rewrite this as x minus x naught equals 1/2 at squared plus v naught times t. And now let's solve this for position. This is a position function, and like any position function, if I take its derivative, I should get a velocity function. So here we go. We go term by term. So starting with the first term, we are taking the derivative with respect to t. So a is a constant. Bring the 2 down, times 1/2 times a t to the 2 minus 1. Go on to the next term. This is v naught t to the 1 power. So bring the 1 down. V naught is still there, and t to the 1 minus 1. Now, x naught doesn't have a t in it. It's a constant. But again, you can imagine that there is a t to the 0 power. So we bring down that 0, and it doesn't really matter what's left, because everything will be zeroed out. This is our velocity function. But wait, simplify this. 2 times 1/2 is just 1. So this is a t to the 2 minus 1 power. That's just t to the 1 power. Plus, t to the 1 minus 1 is t to the 0 power. So that term goes away because it's just 1. I'm left with v naught. This is our velocity function from our position function. Now, I know you already know this because it was sitting right here the whole time, but I wanted to give you some evidence that this clearly works, even if you don't have the theoretical background. Now, let's talk for just a minute about antiderivatives. Gave you the polynomial rule for derivatives, but going backwards shouldn't be that much different. If the rule for derivative says bring down the exponent, and then take 1 away from the exponent. The rule for the antiderivative must be pretty straightforward. Let's see if we can figure out what to do to go backwards. Now, I'm going to leave out the symbology that follows along with antiderivatives because it's pretty confusing in the beginning. And I'm just going to write antiderivative. And I'm going to write with respect to x, just so we have something. But there's going to be some symbols that are going to come up that will actually explain what this looks like. It's the integral symbol. It's going to be a little complicated. We'll leave that to another discussion. But let's say I have a function ax to the n, and I want to find its antiderivative. Well, I want to do the opposite of what I did. And what I did the first time was I bring the n down and take 1 away from the exponent. So I'm going to add 1 to the exponent. And since this was the exponent that had been brought down, I'm going to divide by my new exponent. This is how you find the antiderivative of a polynomial. So consider we had this just a moment ago. We found this by taking the derivative. So now what I want to do is I want to find the antiderivative of v. So finding the antiderivative means going backwards. So this time we're finding position from velocity. If finding the derivative of position gave us velocity, finding the antiderivative of velocity gives us position. So I want the antiderivative with respect to t of 18 t squared plus 24 t to the negative 3. Well, again, this is our plan. We're going to go term by term. First term, take t and add 1 to the exponent. Now divide by my new exponent. All right, good. Let's go to the next term. Take t, add 1 to the exponent. Now divide by the new exponent. This is going to be my position function. Now let's clean this up some. Okay, so this is going to equal, let's see, 18 divided by 3 is 6, t to the third. Let's see, negative 3 plus 1 is negative 2. 24 divided by negative 2 is negative 12, t to the negative 3 power. Well, as luck would have it, I happen to have what we started with. That's what we started with. We did this a few minutes ago. Notice they are very similar. There's only one problem with doing this, and I want to explain what that problem is right now. If my original function had a constant, when we took the derivative, that constant would have disappeared. So whenever we take the antiderivative, we have to add a constant. I'll explain more about what this constant means in the coming days. So we're going to do one final example. Let's say I have a velocity function that looks like this. I want to find the position function and the acceleration function. So remember, going this way, you take the derivative. And going this way, you take the antiderivative. So let's take the derivative first. I think it's easier. So bring the 2 down, subtract 1. Done with that one. All right, there's no number here, so there's a 1 there. Bring the 1 down. Subtract 1 from the exponent. Okay. And there's no number there, so that's t to the 0 power. So that should be plus 0. All right, we're done. Clean it up. 6t plus 6. T to the 0 means it's just 6. That's my acceleration function. All right. Let's go the other direction. All right. Add 1 to the exponent, and now divide by my new exponent. All right, did it. All right, go to the next term. Add 1 to my exponent, and divide by my new exponent. Great. And now, I have no t here, so this has got to be t to the 0 power. So let's see how that works. It's going to be t to the 0 plus 1, and then 9 divided by 0 plus 1. All right, so those are my terms. But remember, whenever you take the antiderivative, you must add a constant. Now let's clean this up. This is 3 divided by 3, or t to the 3rd power. This is 6 divided by 2, so 3 t to the 2 power. This is 9 divided by 1, so just 9 t plus a constant. All right, so what we have done is we have built a set of relationships starting with velocity and getting the rest of my motion equations. Now, there's more to do here. I don't want to belabor it too much. Some of the smart people in the room are probably recognizing that this constant has meaning that seems pretty clear. It's going to be the position when the time is 0. We'll probably see some more of that kind of stuff as we move forwards. But this stuff isn't so bad. You have some homework that has this in it. Give it a try. We're going to talk about it for the entire class period tomorrow.